Okay, any questions to start with? No. Then let me start with so if I asked you to draw the orbital picture showing the orbitals and the sigma bonds and the pi bonds for this, can we do that? Okay. Can you get started? Or, I mean, do you know where to start from? All right. Then let's do this. Let's try this. You can work with a person next to you, or I suppose if you want to rotate your chairs around. But let's see how far we can get with this. And I'll walk around and help. And we'll see how far we get. Okay, so do we have Lewis dot structures for both of these? So for CO2, so if I'm drawing the Lewis dot structure for CO2, what should I have? Oxygen has how many lone pairs? 2. The other oxygen has 2. What kind of bond between C and O? On this side. Okay, for sulfur, lone pairs on oxygen. 2. On this oxygen. 2. What bond between sulfur and oxygen? Over here, lone pairs on sulfur. 2 electrons, 1 lone pair. Okay, so what's different about these two structures? Sulfur has a lone pair that carbon doesn't. Okay, so first step is we've got to draw our Lewis dot structure. You might say at this point, what about resonance structures? In theory, it won't matter because the resonance structures, because all the atoms have to be in exactly the same geometry, it won't matter because the atoms won't move. Because our next step is, once we have a Lewis dot structure, what should we do next? Now let's put this in its VSEPR geometry. Right? We have to identify the VSEPR geometry. So what's the VSEPR geometry for CO2? What's the VSEPR geometry around the central atom? Linear? How did I know that? And before that, how do we know that the carbon is linear? So in other words, we have what hybridization? This is sp hybridized. So we've got to get the central atom, we've got to determine what its hybridization is in order to determine what its VSEPR geometry is. Or you could just do the VSEPR geometry directly. It's got 2 single bonds. What about the sulfur? Trigonal planar, because the sulfur is sp2. So sulfur's sp2, which means that it is going to be trigonoplanar. So we should draw it like this. There's really not a bond to the lone pairs, but it looks like that. So now we have to do the Vesper geometry because that's how we're going to determine whether it has a dipole moment or not. So is CO2 polar or not? It's nonpolar. So in order to be polar, what do you need? A polar covalent bond and an overall molecular dipole moment. Does carbon have polar covalent bonds? Yes. Does it have an overall dipole moment? No, because the bond dipole going this way and the bond dipole moment going that way cancel each other out. So this is where the symmetry of the molecule is oftentimes what we use to determine whether it is or isn't polar. If the symmetry is perfect, it's nonpolar. If it's anything but perfect, then it is nonpolar. Sorry, it's polar if it's not perfectly symmetric. So in this case, it's perfectly symmetrical. Right. Now for the sulfur, is the symmetry symmetric? The symmetry would have to include that third sp2 position. So in this case, we'd have to know which one is more electronegative, and oxygen is above sulfur, so oxygen is more electronegative. So the bond dipoles would go in this direction, but lone pairs we don't do anything with. There is no arrow for a lone pair. And a lot of general chem books, there's debate as to whether they put those arrows in or not. Those arrows should not go there. So we're looking at kind of the molecular geometry. And so in this case, do those bonds dipoles, do those bond dipole moments cancel? No. And so the net dipole would look like this. What does that mean? I sometimes will put pluses on the end of my arrows to remember that that's the plus side. And so that means we're around the oxygen is delta minus. And then around the sulfur up here would be a delta positive charge. And if you're saying, but there's electrons there, yeah, no, that's not, the electrons don't play a role. It's the unequal sharing in the polar covalent bonds. And so would this one be polar? Yes. And this is a nonpolar. So those are the steps we have to go through to determine whether what type of intermolecular force the molecule undergoes. So nonpolar molecules all undergo dispersion forces. Those terms come back, and the idea of London dispersion forces versus induced dipole is what they're sometimes. Those terms are like, they're in style one year and then they're not in style the next. So it doesn't matter whether you call those induced dipoles or London dispersion forces. The London is Fritz London. I went to graduate school at Duke, and the lecture hall was named for Fritz London. I'm not sure what he did there, but he has a lecture hall named after him. Or did, before they tore it down. I'm sure there's another Fritz London lecture hall somewhere else. So dispersion between two nonpolar molecules, and then between two polar molecules. So between two SO2 molecules, our strongest force would be dipole-dipole. So the strongest force between two of these molecules would be dipole-dipole. The stronger dipole-dipole force would be hydrogen bonding. Okay. And so for hydrogen bonding, the only thing we have to kind of remember is that So let's say I have two methanol molecules. Methanol is wood alcohol, it's CH3OH. So if I have two of those, how can I hydrogen bond the methanol molecule? Well, I could hydrogen bond the methanol molecules like this. So in a hydrogen bond, you need to have an atom attached to the hydrogen, and that atom has to be an O, an N, or an F. And then the hydrogen bond is the electrostatic attraction between the hydrogen and another O, N, or F molecule. Okay. So the oxygen is delta minus, the hydrogen is delta plus, this oxygen is delta minus, and so that's what sets up the hydrogen bonding, is the electrostatic attraction between the H delta plus and the O delta minus. So this, with the dotted line, that's our hydrogen bond. So that means that for hydrogen bonding, you need an X atom attached to the hydrogen. Then the hydrogen bond is to another X atom, where X is N, O, or F. So the X's can be any of those three elements, but they only can be those three elements. Okay. And why is that? Because the electrostatics. So let me take a step back. How would two sulfur dioxide molecules interact in dipole moments? Well, if you imagine you have the sulfur dioxide molecule here, this side would be delta minus, this side would be delta plus, and so the delta minus side of the molecule would then be attracted to the delta plus side of the other sulfur dioxide. So you'd have like a shape with a delta minus, a shape with a delta plus, and they would be attracted to each other. And I think in one of the answers that I gave, I showed my iPad with the molecules in sort of color, and so you can kind of imagine that. I didn't bring my little projector thing this morning, so. But it's, and I hope I have it for this afternoon, so I might do it in this afternoon's class. If you were curious as to what I do in the afternoon class, you just go to YouTube, and that's where all the videos are. You don't, by all means, you don't have to watch 2 lectures, but there might be something there. I don't know. It's there.
How do you see the homework answer videos?
How do you see those? That's a good question. Let's see if I can show you that. What I need to do is record a video on that. Because there's one of 2 ways to do this. So, first of all, we need Canvas, because I said I was going to do that. Okay, so let's go into Canvas. Actually, you know what? Since I'm recording this right now, maybe I'll post this. So here's how you do it. First of all, you need to have Flash. No. You need to have. Why are we not logging in? Because it's going to be a bad day. Okay. Yeah, whatever. Okay. So what you do is you go to one of the answer keys that says, so let's say, okay. drawing problems, practice problems, drawing problems, answer key. So you click on that, it goes to this link, which then goes to my Evernote account. And then what you have to do is you have to actually physically download this onto your computer, whether it's your Mac or your PC. So I would do this. Now it's going to load, it's going to try and load it up. If I click it down here now, it's going to try and load that into the browser, whatever you're using, and this won't work out of a browser. So what you have to do is you have to go to an Adobe Acrobat Reader DC, which I have here, and you have to make sure you download the latest one. And then what you would do is you would say File, Open. This better work. Now that's in my downloads on a PC, so it's actually right there. So when I open it up, I see it says 3D. I have no idea what 3D content is, but I should probably enable it. So trust this document always. And there should be down here a player to allow you to play it. Okay. If that doesn't happen, I'll record a video. Because if that doesn't happen, then you have to go to LiveScribe. You have to go to the LiveScribe player and then throw it up into the player. These formats have become, well, I'll post a video and then I'll send you an email. It might be this morning, it might be this afternoon. So, okay, I did not bring practice problems for Friday, so I will bring practice problems on Friday for next week. Okay, so go ahead and read the next sections. If you have any questions, throw them up on Piazza.